In this section we're going to graph ellipses and hyperbolas. Now the equation for an ellipse that's centered at the origin looks like this. X squared over a squared plus y squared over b squared is equal to 1. The x-intercepts will occur at a and negative a because when I let y be equal to 0 in this equation, I have x squared over a squared is equal to 1, so that means that x is going to be plus or minus a. The y-intercepts occur at b and negative b because when I let x be equal to 0 and solve the resulting equation for y, as you'll see when we do an example, y comes out to be plus or minus b. Now, an ellipse and a hyperbola have similar equations. The only difference is this subtraction sign here for the hyperbola, whereas an ellipse has an addition sign. X squared over a squared minus y squared over b squared equal 1, or, since subtraction is not commutative, another equation would be y squared over a squared minus x squared over b squared is equal to 1. Here we have x-intercepts at a and negative a, but no y-intercepts, and you'll see this when we get to the board and do an example. This one has y-intercepts, but no x-intercepts. So, similar equations, but as you'll see, some pretty different looking graphs. Let's take a look at our first one. This first graph is the graph of x squared over 16 plus y squared over 9 is equal to 1. Now this is the equation of an ellipse. Let's just see what the y-intercepts will be by letting x be equal to 0. When x is equal to 0, I have y squared over 9 is equal to 1. That implies that y squared is equal to 9, which means that y is plus or minus 3. So you can see that when x is equal to 0, y is plus or minus 3. So x is 0, y is 3. X is 0, y is equal to negative 3. Now I can find x-intercepts by letting y be equal to 0. When I let y be equal to 0, I have x squared over 16 is equal to 1. This means that x squared is going to be equal to 16, so x itself must be plus or minus 4. So over here I get x equals plus or minus 4. So those are my x-intercepts, positive 4 and negative 4. Now I connect these points with a nice smooth curve, and the thing that I get, sort of an elongated circle, and what it's called is an ellipse. Now there's much nicer, more accurate pictures of ellipses in the book. It's a little hard for me to draw this on this paper right here. But you see, you get the idea here that the x-intercepts occur below the x squared term. They're plus and minus the square root of this number. The y-intercepts occur below the y squared term. They're plus and minus the square roots of this number, positive 3 and negative 3. That's when the ellipse has the standard form x squared over a squared plus y squared over b squared is equal to 1. So this is standard form for the equation of an ellipse that's centered at the origin. Notice the center here is at the origin. Let's look at another example. Now this one is not written in standard form, and I can write it in standard form by getting a 1 right here. I'll do that by dividing both sides by 16. When I do that, I have x squared over 16 plus y squared over, dividing 8y squared by 16 gives me y squared over 2, and that's equal to 1. So that means that my x-intercepts will be at x equal plus or minus 4, that's the square roots of this number, and my y-intercepts will be at plus or minus the square root of 2. Because this number is 2, its square root is plus or minus square root 2. Now, plus or minus the square root 2, that's going to be about 1.4. Let's put that down. Okay, so I'm going to graph x equal plus or minus 4. That's right here and right here. And then y is equal to about plus or minus the square root of 16, or plus or minus 1.4. So let's put, y right here, 1.4 and negative 1.4. So here, this ellipse has this sort of shape to it. And again, there's much nicer, more accurate pictures of these ellipses. I can't even get through that point in the book. So it'll be sort of a football-shaped thing. It looks like this. This blue graph right here is the graph of this x squared plus 8y squared is equal to 16. The red graph is the graph of x squared over 16 plus y squared over 9 is equal to 1. Let's look at our next example. Okay, now the next problem I want to graph here is y squared over 9 minus x squared over 16 equal 1. This is the equation of a hyperbola. Now notice that we have y-intercepts because if I let x be equal to 0, then I have y squared over 9 minus 0 is equal to 1. So then y squared, or y I should say, is plus or minus 3. So when I solve this equation for y, I end up with y equals plus or minus 3. So my graph is going to cross the y-axis at 3 and also at negative 3. Now if I let y be equal to 0, just to check and see if I have any x-intercepts, I get negative x squared over 16 is equal to 1. Multiply both sides by negative 16, and we have x squared equal negative 16, which is no real solutions. So there's no x-intercepts. If I solve x squared equal negative 16, I get complex solutions for this, so I can't use those in my rectangular coordinate system here, so there are no x-intercepts. If there were x-intercepts, that is, if this was an ellipse, and this was a plus sign right here, I'd have x-intercepts at 4 and negative 4. So I'm going to put those in anyways. They would occur here and here. Now I'll show you how to draw the graph of this ellipse. It requires that we draw a little box in here, connecting the intercepts with what would have been x-intercepts if this had been an ellipse. Okay, it looks like that. Now what I do is I connect opposite corners of this box with straight lines. Okay, so I get this line right here and this line right here. Now it turns out that those lines are asymptotes for the graph of this hyperbola. And the hyperbola goes through this point right here, and then it comes around and approaches these asymptotes in both directions right here. So the red graph that I'm drawing is the graph of the hyperbola y squared over 9 minus x squared over 16 is equal to 1. Now notice that if this was a plus sign right here and this was the graph of an ellipse, that ellipse would have x-intercepts here and y-intercepts here and here. And it would be that football-shaped thing that would lie inside this rectangle. When I change this to a subtraction sign, what it does is throws that thing, sort of turns it inside out, and I end up with this curve right here that just crosses the y-axis and approaches these straight lines asymptotically. That is, it gets as close as you want to them but never touches them. Let's try another one of these graphs. I'll put this one in standard form by dividing both sides by 4. I have x squared over 4 minus y squared over 1 is equal to 1. Now because of the subtraction sign here, I know that this is going to be a hyperbola. Now I have x squared first divided by 4, so if I let y be equal to 0, x is plus or minus 2. So it's going to cross the x-axis at 2 and also at negative 2, so I'll put those dots in. It's not going to cross the y-axis, but if it was an ellipse, if it was a hyperbola, if this was a plus sign, it would have intercepts at 1 and negative 1. So I'm going to put those in and use that to draw this box. So I draw the box that looks like that, and then I'm going to connect opposite corners with a straight line. So I'll get something that looks approximately like this. It's hard for me to tell looking at an angle there, but we'll just do the best we can. And those two blue lines that I've drawn in, those are asymptotes for this graph, and the graph is going to cross the x-axis here at 2 and at negative 2, and it's going to approach this asymptotically. So this hyperbola has this shape to it. So the red graph is the graph of this equation right here. It's called a hyperbola. I use this little box in here that crosses the x-axis where I have intercepts, where I would have intercepts if I was graphing an ellipse, and then I draw that box in, connect opposite corners like that, and I get the two asymptotes for the graph. So knowing what the intercepts are and that these two blue lines are asymptotes, I can draw the graph of that hyperbola pretty simply.